I'm pretty sure that by now you're convinced of the inevitability of multiple inheritance, but still for this second segment, let's look at one more example, which I believe is very elegant. It's the notion of composite figures. So the question is going to be, how do we model this important notion in an object-oriented decomposition using classes? We're talking about composite figures. In any system that supports graphics, for example, here I'm using PowerPoint, I can actually apply this mechanism. In any mechanism that supports graphics, any reasonable one, you have this ability to group some figures. If you do this, then it means that here using the group mechanism of PowerPoint, you can decide to treat a whole set of figures as a single figure, and so from now on everything I do with these figures is as if they constitute just a single figure. So it's the notion of composite figure, and of course if you group, you can also ungroup here. So PowerPoint has this, it's just an example of a tool, but in general any reasonable tool that enables you to do graphics is going to enable you to decide at a certain point that a certain set of figures should be treated from now on as a single figure, known as a composite figure. So that's the notion that we're going to try to model. And for example, we could have a set of simple figures like the variants shown at the top. We have a few segments, a few instances of the class segment. We have a rectangle, we have a circle, we have a square, and we could, for example, take a square and a few segments, and that gives us a wheel, and then we produce another wheel, and so we have two composite figures. We decide here that each wheel is going from now on to be treated as a single figure, so it's a composite figure, and then we may add some more figures to make up a more sophisticated figure. In that case, at least I hope that's what it's supposed to represent, a bicycle. How do we represent such a notion? Well, the answer is really very simple. What's a composite figure? There are two parts to this answer, or two complementary answers. One is to know that a composite figure is a figure. We have seen examples of geometric figures as modeled in software before. A figure is an object with features, here queries and commands all together, not separated. Queries such as center and display, and then commands such as hide this figure, rotate this figure, move this figure by a certain horizontal and vertical displacements. So that's the notion of figure, and a composite figure sure is a figure. On the other hand, a composite figure is made of a number of elements, like our bicycle, which was made of a bar and two wheels and some other elements, and the wheels in turn are made of circles and segments. So that's what it is. We could model it as a set. Let me model it as a list, meaning that we remember the order in which we selected the elements of a composite figure. So a composite figure is also a list of figure in the same way that it is a figure. This is a quite typical example of multiple inheritance, and of course we could always use delegation, maybe on one side, maybe on the other side, but it wouldn't quite cut it because there is no particular reason to favor one of these viewpoints over the other. A composite figure is as much a list of figure as it is a figure. In particular, it has all the features of lists, such as queries like count, which gives us the number of elements, or like item, which enables us to access a certain element of the list, and commands such as put or remove, which allow us to add an element, say a figure, or remove a figure from a composite figure. So there's no particular reason to favor one of these viewpoints over the other. And in fact, if we have such a notion, it's going to be, we can add it to the inheritance hierarchy that we might already have for figures. You may remember from previous lectures that we had assumed that one of the possibilities for figure was open figure, another one was closed figure. Now we have a third one, which is composite figure, which however also inherits from list of figure. So this is how we are going to write the class. Class composite figure inherits from figure and inherits from list of figure. And then this is where things become, I think, really elegant. When it comes to writing individual features of the class, typically these are deferred features inherited from class figure, like display, which we now need to implement to effect in class composite figure. So how do we effect display? Well, we have to take the whole list of figures, which we are, because we are a composite figure, and this means that we are also a list of figures, and for all these we simply are going to apply the feature display from start, meaning begin at the beginning of the list, until after, meaning until we have exhausted all the elements of the list. We are going to do force to move to the next element, but before that we do item.display. Item is the current element of the list, the current figure, and we apply display to it. What we are using display in the body of display? Yes, well, it's not necessarily recursion. It could be recursion if we have some elements in the list that are themselves composite figures, but in general it is not the same display. Display, remember, is a feature that is available for all figures, composite or not. So whenever we take item represents a figure, and that figure could be a circle, could be a rectangle, could be a segment, or it could be a composite figure, and in any of these cases it will have its own feature display. So clearly this can only work with dynamic binding, and it could be recursive, but it's only going to be recursive if an element of a composite figure is itself a composite figure. If you remember the example of the bicycle was made of certain figures, but two of these figures, the wheels, are themselves composite figures. So in that case, when we get to this particular element, the first wheel, or that particular element, the second wheel, the display feature that we find in the application of dynamic binding is going to be exactly this display, called recursively. On the other hand, if another figure of the bicycle is, for example, a bar, then there's nothing recursive here. We do apply dynamic binding. I found this example really elegant, and you can see that it's kind of a concentrate of much of what we have seen so far in this course. We have classes, we have inheritance, specifically multiple inheritance. We have, of course, genericity, because we are talking about a list of figure. We have, in fact, a polymorphic data structure, because a list of figures here is going to contain figures of different types, like segments, like circles, like composite figures. We have dynamic binding, without which none of this would work, and we also have recursion. So it's kind of a concentrate of everything we have seen so far, and I hope you will agree that this is a really elegant use of the combination of all these techniques. So what we've seen in this segment is another example of fruitful application of multiple inheritance, and it's clear. You can write it using delegation, of course. I encourage you to try it, but you will see that delegation doesn't quite cut it. It works, but it's much less elegant than this simple technique based on straightforward application of multiple inheritance.